Hello guys, welcome back. Today we are going to discuss about a simulation setup in Flubio. So the aim of this video is just to provide you some guidance, step-by-step guidance to uh, the operations needed in order to set up effectively simulations. So we can jump inside the tutorial I prepared for this video, which is included inside the Flubio examples, and in particular if you go in this folder, Flubio Poisson, Untitled Grid, you will have all the files you need, and you can start experimenting on your side as well. So first thing first, we would like to see the geometry we are going to simulate today. As you probably know, the mesh is stored inside the grid folder, where basically we just have an empty folder, which is the one with the binary files once the mesh has been read, and then a serial folder. And in the serial folder, if you follow the tree, you will find basically the mesh. We have two kinds of meshes here. We have the original one, which is the one in open format, which is the usual format with boundary faces, owner, neighbor, and so on. And then we have the mesh used effectively by Flubio, which is basically the same. The only thing is that Flubio's mesh is just a bit cleaned up from all the C++ specific syntax we do not accept. And you can generate the serial mesh in the open format using the mesh you prefer. Up to now, basically every mesher can output in this format, or if you want, you can copy one from your favorite OpenFOAM case and just convert it following the instruction into the manual or in one of the videos or we have in our website. So once you have the grid inside the serial folder, then you can visualize your geometry, and you just have to run Flubio Mesh View. And Flubio Mesh View is basically a tool which reads the grid stored inside Flubio files and converts this grid into a VTK format you can open in ParaView. So if you just click enter, you see you have basically done your conversion, and what you can do is open up ParaView and then just open and then go into this post-processing folder, VTK fields and mesh, which is this one. So you see it's this particular shape. The mesh it is triangular and fully unstructured. It's not particularly good or fancy. I just done a quick one just to show you a bit all the procedure. And okay, so this is the grid. Pay attention that you need to put at least one cell in the third dimension, because as OpenFOAM does, Flubio as well is fully three-dimensional, and so we just cover the 2D or the 1D dimensionality as particular case, just imposing one cell in the direction we don't want to solve, and then applying a proper boundary condition there. And so this is the mesh. There is nothing more to explore, so we can go back, and what we can do now, we can do two things. We can copy the serial mesh inside processor 0 folder and run serially, or as I will do today, we can run in parallel, which is always a good option. But before doing that, we need to decompose the mesh. So as you might have seen, we have now a brand new mesh partitioner. So you don't need anymore to use the composed path from OpenFOAM in order to get the composed mesh file, but you can decompose your mesh directly here in FLUBIO, starting from the serial one. And doing that is easy as calling this script. So the composed mesh -h -h will show you how to use it. You have all the help here. You can take a look at the video we did a few times ago explaining this new partitioner. I would like to put just a warning since this is a new feature, and yeah, we are going to improve it or debug it as far as needed. But as far as we have tested, it looks promising tool. So you can just do this, the compose mesh, then -t. You can specify the library you want to use to decompose your mesh. In this case, Metis, which is our default. No, which is not our default, which is an option we have. Our default is Caip, which is a similar tool to this one. And after that, you have to specify the number of partitions you want, which is -s. S stands for subdivisions. We are gonna use 4 since this mesh is small case but not small as others. So we are going to run in parallel all on the laptop. This is everything you need to do. If you want to run in parallel, you can, and then you can just, for example, add -n, and then I don't know, 4 processors to run in parallel, and -p to activate the parallel run flag. Since we don't need to, the mesh can be decomposed effectively even in serial, so we just go with this. If we press enter. Okay, so we have done it already, so it's quite fast. We have improved a bit this utility since last time, and basically what you can see is that in here you have all the loggings, so how effectively your mesh has been decomposed among the processors. You can view, of course, the partitioning. This is quite important, so remember to do so, because sometimes partitioning is just not good enough, and you need to tune a bit the options or the flags for Metis or Caip to get better results, but in this case, I think should be good. So if you want to visualize the partitioning, what you have to do, you can just npm run -mp4 because we have 4 partitions, and then this tool, which is called FLUBIO Mesh View Parallel. So FLUBIO Mesh View and FLUBIO Mesh View Parallel, as any other tool which has appended the suffix parallel, it means that basically it does the same thing of mesh view, but this time we do it in parallel. So basically now every process will read the mesh we have decomposed, and will show us basically also the field, which is the self distribution we get from Metis. Sometimes for bigger cases, the parallel versions of tools is faster because you have to think that those tools basically works using the decomposed mesh. So every processor does its own partition. Otherwise, if you remove the flag, you basically are requiring to FLUBIO to reconstruct the serial mesh from the parallel, and then gives you the result. So the interface, you don't need any flag. You just run like that, and that's it. You can open parallel view again, and this time, if you go into the parallel folder here, we like to store there the parallel decomposition results, just to avoid confusion. You go in mesh, and then you see you have several files. You have the 4 partitions and 1 PVTU file linking them together. So if you click OK, we can now delete this, which is the old one. You see you have exactly the same mesh. But this time, if you go here, you will see you have a field you can display, which is called cell distribution. You click it, and you can see your partitions with different colors. So this is the mesh we are gonna use, and the composition is this one, and there is really nothing more to say. Okay, so now we have a serial mesh, which is coming from your favorite tool. We have a decomposed mesh that we can use to run in parallel, which comes from our decomposition tool. And then the only thing left is just to setting up the case. So let's start from the boundary conditions. Boundary conditions are inside DC's folder, and you are just one file which ports the number of the field, the name of the field you're going to solve, and then just append DC just to highlight that this is a boundary condition file. If you click it, you see just a simple text file, and inside you have a JSON dictionary. Why do we use JSON then? Because it allows us to get rid of the formatted input, which is a bit of a pain in Fortran. In this way, we can just set up our boundary condition with many lines, with many options, without care about all the file formatting, because we have an interface with a very good library which is called JSON Fortran, that basically can parse a dictionary in this this format here, and basically store it as an object inside Fortran. You can then go inside and get all these information in quite cool and easy way. So as you can see, we have several boundary conditions. We have the front and back face FB, which are this one and the one in the back. And then we have bottom, sides, and top, which of course are bottom, and then the sides and top. Boundary conditions are in the bottom, fixed value of 1, in the top, fixed value of 0, and for the side walls, we have a 0 gradient, which we call normal 0, which means normal boundary condition 0 value, which basically means that your walls are adiabatic. As you can see, our boundary condition, it depends which one you do, but you have always a type which targets basically the boundary condition you want to apply, and then we have a value. This value is not always mandatory. For example, in this case it is, because we are fixing a value and you want to fix 1. In this case, normal 0 doesn't require a value, but we have it anyhow, but you can put whatever, it doesn't matter, the code won't use it. And so it's quite simple, and you can fix an internal field if you want. Internal field, the nice thing, it can be a number, or it can be an expression, depending of coordinate system, for example, x, y, and z. This is quite cool, so you can initialize your field in a bit more with a bit more freedom. So boundary conditions are all here. They are correct, or we think so, at least. And then now we can jump back to the settings folder and start setting up our dictionaries. So minimal dictionaries are these 3 or 4, it depends. Steady state controls, it's a dictionary we are not going to use today because it is something related to the steady state computations, but today we're gonna run transient. So it is here because in this tutorial you can run either transient, either steady state. So it's just here for convenience. And then you have other 3. So the first one is simulation controls. Simulation controls is the dictionary where you usually fix your favorite settings for the simulations control. The first one is the time step. Today we are going to use this one, 5e-2. Then you can fix the maximum time for the simulations. You can fix the maximum number of fields to save. In this case, 200, because we're gonna do a movie. and then you can set up also a saving frequency, so this means 10. So since the time step is 0.05 and we have set save every 10, this means we will have a field after 0.5 units. So remember, Fluvio, it's not aware about dimensions of things. It can work implicitly non-dimensional, as in this case, for example. So you don't have to assign dimensions to things, but you of course need to know what you're going to do. So this is how we work. OpenFOAM, as you know, fixed dimensions. Sometimes this is a bit of a pain, because when you just wanna simulate your equations in a more mathematical way, you maybe don't care about physics, you don't care about dimensions, you just wanna solve Laplace equation, for example, using or Poisson equation using some coefficient mu in front of Laplacian, and so on. You don't need to specify dimensions. So be aware. This is a knife. This is something that can come back and bite you if you are not if you do not know what you are doing exactly. So that's a warning for you. And then you can also start the simulation if you want. You have just to put here the number of the time steps you wanna start. And so this is quite easy. Other things, after we have set the general contours of the simulation, we can specify our discretization settings, which are found inside the relevant dictionary discretization options. And this dictionary is done is not like that. So basically you have a default dictionary where you can put inside default settings. So those settings, so everything you put inside default will be used from every equation you have in your model. So this means that if you have not just the T equation for the temperature, but maybe you have another equation for something else, that equation will use this discretization, this time scheme, this diffusion term scheme, and this gradient. Otherwise, if you don't want to apply the same settings to all the equations, you can specify inside this dictionary. Just after the default dictionary, you can just say, okay, I wanna for the T equation, I wanna change something. For example, I wanna do time scheme, another one, for example, this one, okay, which is the backward time scheme, second order accurate. And you can do, yeah, you can add other things as well for all the entries you find in default, and you can do the same for every equation. So if you have another equation in your model, for example, I don't know, A equation, then you can do the same. So you can specify another one, time scheme is equal Euler again, for example, and so on. So the good thing of using this JSON format is that if you put something does not exist in the code doesn't care. The code just targets things it finds. So if you have not defined the A equation, your solver, yeah, the solver doesn't care. It doesn't read these entries at all. And other things you can set, and which is quite important, is the non-orthogonal collections number. In this case, we just use 1. You can do more non-orthogonal collections. You know that in finite volume method, orthogonality is quite important. It has a quite important impact, and so you can collect your orthogonality by iteration. And here you set the number of iterations you wanna do. Okay, this looks all good. And finally, you can define your solvers. In this dictionary, you have one entry for every equation, and for every equation, you can specify your settings. So The settings you usually need to specify are the solver you're going to use, this and the preconditioner as well. Those solvers and preconditioners comes from PETSC, as you already know. And so here you just have to put the name, in this case is CG, which stands for conjugate gradient, and the preconditioner we use B Jacobi, which stands for block Jacobi, which is a kind of incomplete LU preconditioner. You can change it using, for example, multigrid from IPRI, and you just do IPRI. The names for the solvers and the preconditioners are the same you find in PETSC, so we haven't changed the name, so the interface to the solvers is the same as defined in PETSC, so same names. Yeah, let's use block Jacobi in this case. And after that, you can set tolerances, both absolute and relative. In this case, I just set the absolute one and relative to 0, but you can set both as control stopping criteria for your solver. And you can do the same thing for other equations. So if you have the A equation, again, you copy this block, you put it down, you specify what you want. General options apply to every solver. So we have basically the maximum number of iterations before the solver stops, and this is set to 10,000. Open form is set to 1,000. So basically this means that if the solver is not converging after this number, it will stop. It will tell you that basically the solver doesn't converge because the number of iterations is exceeded, and this is usually a warning that something is going wrong, because if you don't converge within 10,000 iterations, maybe something is not going in the right way. A compute preconditioner is a flag which applies basically to Laplace Poisson equations and pressure equations. Basically, it lets you specify after how many time steps or iteration you wanna to recompute the preconditioner. So basically, lets you use the previous time step preconditioner, and this is done for an iteration, and then for performance reason, because sometimes computing preconditioner is expensive. So if you, in this case, we recompute the preconditioner every time step, but for example, you can ask to recompute it after every 2 or every 5 or every 10. That's really a flag that depends on your physics. It depends on the equation you are solving. So there is not a correct answer. If you are in doubt, just put 1. So it will compute the conditioner every time step. And then we have nothing else relevant. So now we are set up everything. We can just close. The only thing left is just to review a bit the coefficients in our equation. So FLUBIO-Poisson solves Poisson equation. In this case, there is no source term, so we're just going to solve the time derivative of temperature minus the Laplacian of the temperature times a coefficient, which is the diffusion one, equal to 0. And the coefficients of the equations, which are proper fields, so they can in general change in space, for example, are stored inside physical constants dictionary. Here you have just 2 entries. We have mu, which is the diffusion coefficient, multiplying the Laplacian term, and we have also rho, which is the coefficient which multiplies the time derivative of temperature, which is 1 in this case. We don't need to do anything special. Okay, so this is how you set things. Now, since everything is set up, you can run. In order to run, you need to be in the case folder and then invoke the mpi run command, and then the name of the solver, which is FLUBIO-Poisson. And then you can just click enter. Then you see is computing the solution. It will be quite fast. We put 20 as maximum time, so we are 10 already. So it's just a matter of a minute or so. yeah, the simulation is done. 24 seconds. So now you see you have for every iteration a bit of logging. You have the time and the iteration number. You have the number of iterations to converge the T equation, and then the number of, the number of iterations you need to converge the same equation, but meanwhile the orthogonal correction is applied, and then you have the initial norm and the final norm. You can specify which kind of norm you want, so you can use both the normalized one or the absolute unnormalized one. It really depends on you. In this case, I think we're just using the normalized one, so we don't normalize our residual. Yeah, so it's just not important here because the case is anything special. Now the solver of course saves fields meanwhile it runs, and those fields are inside post-processing fields. As you can see, you have many folders here. If you just jump inside one folder, you will find some files which are in binary format. You have time.bin is a file storing information about time step number and time step value. So it's just a very small file storing this information. And then you have the fields file, which are called t-d and then a number. This means basically that you have 4 partitions, 0, 1, 2, and 3, and each of these files is storing the field for target partition number. So those files, of course, are then decomposed because we have run in parallel. We can do 2 things. We can reconstruct them and view the field in paraview, or we can just process those parallel fields, those decomposed fields, and again being able to view them in paraview. It's really up to you. It's the same difference there is between mesh view and mesh view parallel. So if you just want to reconstruct your field, so having the serial field, you have to run this utility, which is called FLUBIO-Fields. If you wanted to just produce a VDK file in parallel, then you just do this dash parallel, and then you run under npm run with the same number of partitions you have. And then you have other utility you can use. For example, you can reconstruct just the field and then redecompose it in a different number and so on. And we're going to explore this in a different tutorial. For this case, since it's quite small, we're going to reconstruct the field in the serial one. But there is if the case is bigger, feel free to run under MPI. So in this case, every processor will basically produce a VTK file for its partition only. So the speed up is consistent in doing that. FLUBIO fields. So we would like to reconstruct the field, and if you do minus help this time, you see you have the help. You need to specify something for reconstructing the field, especially you need to specify the number of processors you used. And so let's do it. Minus MP, we used 4 processors, and then you can do different things. You can target a particular time, just 1. You can put the start time and end time and how many fields you want to skip in the mean of those two start and end time steps. Otherwise, if you don't want to bother, you can just reconstruct everything. In this case, you put minus all. So minus all we will induce this program to loop inside all the folders it finds inside the fields, post-processing fields folder, reconstructing the fields there. You can target also just one field among the solver produced, In this case, it's pointless because we just have the temperature field, so we are just one. But you can do it like that, minus fields, and then t. Okay, so this means that FLUBIO fields we just construct a t field. For example, if you run Navier-Stokes, you have u and p. You might for some reason just construct u. Why not? And so you do like that. So you can specify the fields to reconstruct. If you don't put anything, it will reconstruct the default fields it finds in the default fields defined for each solver. So for this solver, which is Poisson, you just have just one default field, which is t. Okay, so if you run it, yeah, you see FLUBIO is telling you, okay, I'm reconstructing this time step number, and so we'll have to compute a few of them. And as you can see, everything is done. So now you can visualize the results in ParaView. So let's delete this. You can just open, and if we go back into this folder, you see that this FLUBIO field star object has been, this group of files has been produced. You can open up independently one by one. Otherwise, ParaView lets you import the whole group, which is what you're gonna use now. It's quite good as function. So we can click OK, and here we are our mesh. So since the simulation is 2D, what I like to do is the following thing: just do a slice. Sorry, which is z normal. Okay. And now we adjust the slice. And then what we can do, we can just go here and select the variable we would like to visualize. In this case, we just have t. Please note that the variables are imported at the cell center, so that's why you have this kind of cube nearby the name of the field. This is because our code basically doesn't know about node values, but just it knows about the cell center value. So you can click it. You can change here your scale, put in another one, for example this one. You can also scale, since we already know that the maximum is gonna be 1, because we put 1, so the maximum is gonna be 1. And after that, if you don't like the thing, these things to have the cell center value, you wanna see a kind of interpolated value to the nodes, you can do it using this tool, which is cell data to point data. This is a fully artificial thing in ParaView. So basically, ParaView will interpolate from the cell centers to the cell nodes, and sometimes this is preferred because you can produce a smoother image, for example, for high quality papers or images you want to share with someone. But from a numerical point of view, the cell center fields, it's better because you can see where bad things, in which cells bad things are happening, or similar tasks. So in this case, we are just going to use the node distribution here we have interpolated, and after that you can just go add one frame, or you can just play your video. You see basically the temperature is from the value 1 is propagating through this geometry, and this is what is supposed to do, right? Because we start from 1, and then we have a gradient of temperature, so the temperature will propagate from the bottom to the top in this way. Okay, so this tutorial is finished. As you can see, Once you have a mesh in the correct OpenFOAM format, is quite straightforward to convert it in a parallel mesh you can use to run, and all the other all the settings are inside the settings folder. You can experiment there. You can go through the tutorials we have, of course, because this is just a minimal example, but you can use other options. You can add more controls. You can require, for example, to save gradients. You can require you can add custom options to your solvers and so on. All those kind of things are of course described into other tutorials, and maybe and probably we can do other video tutorials like that to explain you a bit better. So thank you very much for watching, and see you in the next video. Bye bye.